Hello. I want to cover the second part of Module 3, which is on sampling and probabilities and areas under the normal curve. And this is the kind of information that is specific to the assignment that you're going to complete for this week. So in this course, there's a strong focus on inferential statistics, and let me explain what that means. In general, there are populations of things. There are populations of people. There are populations of aircraft. There are populations of pilots. There are populations for just about anything. And statistics allows us to not have to go through the expense and time of surveying every member of a population. We can take a random sample from that population and perform some calculations, and we can infer from that sample what the behaviors are in the population. So as we move forward through this course, keep in mind that we're going to be drawing samples from a population and then do some calculations and then inferring those results back to a larger population. So I have here the slides for Chapter 4. And I'm not going to go through all of them, but I want to point out some of the more salient points and provide some further explanation for you. So, as I mentioned earlier, this is about the normal curve, and we're talking about drawing samples from populations and then looking at the likelihood that a particular score is representative of that population. So we've talked about inferential statistics, and the normal curve is used throughout statistics in a variety of ways, and it is a very good frame of reference because it seems to be fairly well understood, and we don't have to go into the calculus of the normal curve and how moments about the mean are computed or what that in that mathematical direction. We're going to be in more of an applied statistical analysis. So we're going to be putting things into context rather than into theory. So normal curves are found throughout nature, and there are as many normal curves as there are combinations of means and standard deviations. So a normal curve then is a family of curves, and each member of that family has its own mean and standard deviation. So keep that in mind as you're computing a normal curve, and you may ask the question, well, why is this distribution a lot wider and a lot flatter than another distribution that is more narrow and peaked, and they're still called a normal distribution? It's because that there are an infinite number of normal distributions. And we're going to use our knowledge of the normal distribution by being able to compute percentages and probabilities, and all of that has to do with what are called areas under the normal curve. And we're going to be computing the area under the curve between the mean and infinity, or below the mean, or between a particular point, outward or behind, and it sometimes gets rather confusing, and I want to point to an application that is in the helpful hints for Module 3 and show you how to use it. But I do want to tell everybody that I want you to show your work on the assignment for this week so that not only do you understand what it looks like visually, but you also can connect that to the calculation. So hopefully the three things come together: the problem, the calculations, and the visual representation, and you now kind of understand what the nature of the problem is. So we can use the normal curve table that is in the back of your book. It's also found on the internet, and there are a lot of applications that we can use to compute, let's say, given a particular z-score and areas between a particular z-score and the mean. So in these slides, it goes through a step-by-step method of computing the area under the normal curve. And it always is going to begin with this formula for a z-score. The score minus the mean divided by the standard deviation. And from that, we're going to be able to do some other kinds of calculations about a point from there outward and behind and so forth. So I'd like to go to this application here that is referenced in the helpful hints. And what I have set up here is a normal curve that has a mean of 100 and a standard deviation of 15. And this happens to be the mean and standard deviation of IQs for adults in the United States. And so I'm going to go through some examples of how to use this application. So if I wanted to know, if let's say that I had an IQ of 140 with a mean of 100 and standard deviation of 15, I already know I'm 3 standard deviations above the mean. And people with 140 IQs are rare. And you may say, well, how rare is that? And if you look down here, it says the shaded area, which is right here, is equivalent to 0.0038. Well, that is 0.4%. 0.4% of the population have an IQ above 140. So not too many people in the entire population have IQs that high. If I wanted to look at the area below 85, which would be 1 standard deviation below the mean, subtract 15 from 100, and that tells us that about 16% of the population have IQs below 85. And then if I wanted to look at the area between plus or minus 1 standard deviation of the mean, or between 85 and 115, then that is 68.27% of the population. So we should kind of remember that about 68% of the scores in a population are bounded between plus and minus 1 standard deviation. And then if I wanted to find the percent of the population that did not have an IQ between 115 and 135, then that would be 85% of the population. It's kind of a strange question. I think a more likely question would be to take this example right here and flip it around to 85 and 115. And that just tells us that about 32% of the population have IQs above and below 1 standard deviation of the population. So in the assignment for this week, you're going to need not only to use this as a fallback, but I'm also going to expect that you're going to be using these methods for computing the percentage above or below a particular point in a normal curve. So just follow all of these steps right here, and you should be good to go with the assignment for this week. If you have any questions, then just post it in the Ask a Question for Module 3. And I think that's it. So we'll talk to you later.